Uh, Good morning. As I mentioned in the intro, I work for NMFS. I'm the Caltrans Engineering Liaison. I'm out of the Santa Rosa office, but I work statewide. I'm a resource to all 6 fish packs. The talk I'm going to give today is sort of an update on what I presented at Bridges in Biology last year. And when I put that original talk together, I drew a lot of inspiration from a talk that Mike Love had just presented to NIPS, and also another talk from Brian Kluwer. So I'd like to credit them, and they've both been very gracious and shared a lot of their slides with me. The purpose of my talk today is not really to present you with a how-to map step-by-step for a design process, but it's really to kind of give geomorphic context to the design process, to your future stream crossing projects, and anything that involves channel restoration. So I'm hoping to provide, let you know why Rick and I might be asking for certain aspects in the design process, and maybe to inspire you to collect a few additional pieces of data, include things in your design process, and maybe convince the budget folks to include those as well. Presentation outline. I'm going to talk just real briefly about fluvial processes and channel morphology, just establish some kind of basic parameters. I'll show a few fish passage barriers, talk about a suite of potential solutions. Then I'm going to get into geomorphic assessment and risk, and then discuss geomorphic design approach. I'll start out with kind of a fundamental tenet of fluvial geomorphology, and that's that a river channel, its geometry, its slope, width, and depth, is shaped to transport the dominant flow and sediment load within its banks. We call that the equilibrium state. There is a rhyme and reason to why a channel has its shape. When the equilibrium state gets disturbed, the channel's shape changes. So when you're looking at a river channel and you see some kind of adjustment happening, it means there is some kind of disturbance to the channel system. Sort of a flow chart of geomorphic processes. You start with, often we consider climate and geology in your watershed as independent drivers. They are kind of given parameters that we are not going to change. That moves into watershed controls. And at that point, we're talking about catchment scale processes. We're talking about large scale hydrologic inputs, sediment fluxes, where you are in the watershed is really going to control that. Those come together to produce a flow and sediment regime. Now we're kind of down into fluvial processes and channel morphology. So that's how your flow and sediment regime interact with your channel bed, your banks, your floodplains. Those combine to produce habitat, channel morphology, and habitat structure. And my main point of really this diagram is we often focus and work in here. We care about the habitat and what that looks like. We try to influence fluvial processes and channel morphology. But you have all these upper controls here beyond that, that if you don't really quantify, appreciate, and understand, your channel design is going to have a hard time being successful. So watershed controls on morphology, we're generally talking about channel slope, which we find is kind of what's most correlated to your channel type, your discharge, your sediment supply, both volumetric and the size distribution of that sediment supply. I'm going to kind of, geomorphologists, we love classification systems. There's lots of them out there. I'm going to kind of walk through looking at from a watershed perspective of where you would find different channel types, and maybe you can get a little bit of an appreciation of what the watershed controls are and how that drives what kind of morphology you find. When you're looking at a headwater system up here where your slopes are steep, your sediment flux is high, but your actual hydrology is generally low, you tend to find steep cascade type systems. As you move down to kind of where your first order streams start to come together for second and third order streams, you head into step pools. Step pools are usually in your 4 to 6% range of channel slopes. And again, as I mentioned earlier, by and large, slope is a very good predictor of the kind of channel type you will find. There's a lot of kind of remote sensing done to predict channel morphology using LiDAR and DEMs, and we find that the correlation of your channel type with slope is quite high. So at your step pool system, you still are very coarse sediment, boulder dominated typically. As you move down valley, starting to look at 4th, 5th order type streams, when you're in your 1 to 3% type of slopes, you get the plain bed systems. Plain bed systems, if there's a large input of wood, often these can have forced pools inside a step pool system. And now, when you're looking at 5th, 6th order type streams, your pool riffle complexes are kind of a natural self-sustaining element. Again, if you have large influxes of wood, you can have a higher frequency of your pool riffles and also generally much higher complexity in your pool riffle systems. Looking at larger streams, for folks up here, particularly we are talking now about Sacramento River scale systems. Up to now, I've kind of been talking about where your shear stress, your tractive forces come from, your sediment flux, your hydrologic flux. Those are your erosional forces. When you're looking at a river system, there's also your boundary controls, where this is basically your resistive, what's providing your resistive force to combine to produce your channel morphology. Natural boundary controls are generally the valley confinement, bank strength, and your wood supply. Wood provides a lot of erosional resistance and forcing mechanism. I like to think of a road crossing is often another local boundary control that we put into the river system, and that affects your morphology as well. Of those boundary processes, kind of calling out specifically vegetation, I think it's, in general, very underappreciated as its impact on channel morphology. Vegetation generally does three things. Through wood recruitment, provides a habitat forcing or morphologic forcing mechanism. It is also a sediment storage and scour mechanism. Some systems that you have a lot of gravel trap behind it. But in finer grain systems, this really changes where your deposition happens and your residence time as sediments moving through our system. It's also a key component of bank strength, both directly through root strength, resistance to erosion, but it also provides evapotranspiration, sucks water out of the banks, and increases bank resistance. When you don't have vegetation, you often end up with something like this, or if you had a system that evolved with vegetation and then you remove the vegetation, this is a grazing example on the central coast, kind of near Bodega Bay. Caltrans is looking at, right now we're designing a new crossing right here, but there's obviously issues up here that have changed the natural channel shape and morphology. It's over widened, a lot of sediment depositing out. So as part of fixing this crossing down here, there is going to be a lot of re-veg work happening upstream as well. Moving on to fish passage impediments. Spring Branch Creek, bottom left there. Kind of three classifications usually. We talk about jump barriers, flow depth barriers for swimming, and velocity barriers. These are all primarily examples meant to show jump height problems. All of these, particularly White Chica here, has very inadequate jump pool to actually try to ascend into that culvert. Pretty classic scour of the downstream side of concrete aprons. You see a lot of that. The solution is often to install a bunch of riprap to prevent further scour and structure failure. Spring Branch Creek here has a nice dollop of riprap at the outlet, and often this turns into as much of a barrier as trying to ascend into this and swim through that. This here was an example where they attempted to concentrate flow here with some rail along the side there. Again, still pretty much a jump barrier. Flow depth problems, your concrete boxes, your RCBs here, those are pretty much, in almost all cases, are a flow depth problem at some discharge for swimming through. They tend to unilaterally spread the flow out, so at lower discharges, there's inadequate flow for fish to get through. Corrugated pipes, same thing. Corrugated pipes are often fantastic debris racks at their inlet. If the fish was managed to swim up this, it would not be a good solution at the inlet there. Velocity problems. Here's a pretty obvious one, but my point in kind of comparing these two, you don't need to be approaching near inlet control conditions to really create a velocity problem for a fish to be swimming through. Culverts are generally undersized, often they're placed at an oversteep slope, so you can end up with velocity problems at relatively low discharges for the system. This top example, of all the fish passage impediments, we often find many of them out on site. This one has both a jump height problem with RSP at the outlet, it's got a flow depth problem, and also I know this one tends to have velocity issues at several stages. So that's kind of a really quick overview of looking at fish passage problems. What do we do about those? This is sort of a hierarchy of preferred solutions. These would be in NMFS stream crossing guidelines. DFW has a very similar set of your process of how to figure out how to deal with a fish passage problem. First option, do we need the crossing? Can you take the road out? Really not that applicable to Caltrain's suite of roads, but it is something that comes into play for us for private roads, county roads, forest roads is often something that can be looked at. Beyond that, what do we like to see? A full span bridge, floodplain to floodplain. Essentially getting out of the way, let the river do what it needs to do. After that, we deal with something called stream simulation, which is narrower than a floodplain to floodplain solution, but again, we're trying to, stream simulation generally we're looking at restoring fluvial processes under the crossing. Key component of stream simulation is the crossings at least bankful width. Then beyond that, we talk about an active channel solution. We're dealing with something narrower than bankful width, but again, it's generally a natural bottom crossing, and hoping at least at that point fish can swim through just based on natural bottom hydraulics. Then we have hydraulic designs where that suite of solutions is looking at very closely calculating what your hydraulics are within your crossing, and it's supposed to match whatever swimming, leaping abilities of your aquatic organisms of concern are. Straight to a few examples and additional detail. Here's a full span solution on Up Creek. This is 101 Willits bypass mitigation. Here's what crossing used to look like, a couple of undersized RCBs. You can see scour problems. Also, the sediment did not move through very effectively through this system. Here's where we are today. You can see abutments out of the bankful channel. Bankful channel is roughly right there to there. And right away you can see the heterogeneity of the sediment deposits that are moving through the system. There is a very large, nice cobble bar forming about 2 years downstream of this that I've been told they've seen a lot of successful spawning on this, but a lot of that comes from just reestablishing sediment continuity through this crossing. When you have this kind of system, you're not going to get that nice cobble bar developing right downstream. Here you do. The stream simulation design option. Again, here we're at least bank full width in your crossing. Generally, we like to set, if the crossing does have an invert, set the invert at grade with the stream channel. And the other components of a stream simulation process, you are trying to create a mobile bed within your crossing. You're allowing the sediment within the structure to come out, and you're hoping that it's going to be replaced with natural bed load from upstream. Key component to getting this crossing right is finding a reference reach. In almost all cases, you're looking at something upstream and collecting very detailed information of your reference reach to understand the channel morphology, shape, what kind of forcing mechanisms are working upstream, and replicating them within your crossing. So that is sort of the theory behind how you're going to create a successful sort of active bed that moves out and gets replenished from upstream reaches. If you don't have a reference reach, this approach is kind of extra challenging. Here's an example of a completed stream simulation project, bottomless arch culvert. We're looking at a 26-mile creek up in Washington. Again, here you can see about it. The active channel is wetted up here. You can see a little bit of overbank area, and your bankful channel still is contained within the rock on the edges there. The active channel design. Two main differences between this and the stream simulation approach. It's narrower. Your width is closer to what the active channel width is. And generally, you are trying to make this a static bed. You are designing, because this crossing is narrower than the bankful width, your erosional scour forces are higher than adjacent reaches, so you're unlikely to retain sediment within the crossing on its own. So you take various measures to try to get whatever sediment you put in here to stay. Usually you do this by oversizing the sediment relative to what's around. I'm learning from Chuck that he's developing some additional ideas on how to get sediment to stay here. Other things include putting sediment retention baffles inside, grouting sediment in place. But again, you're essentially trying to create generally a static bed within the crossing. A few examples of active channel solutions. These tend to have much higher success rate in really low energy systems, low slope environments. Long term, it is very hard to keep the sediment inside a system where you know that your width is less than the bankful channel. To go back to kind of that first slide I showed, where we talked about the kind of fundamental tenets of fluvial morphology, that a channel is shaped to transport the dominant flow and sediment load within its banks. Well, if you've narrowed that channel geometry, large flows tend to blow out the sediment that you're putting within your crossing. And I actually don't know if this arch here is a stream simulation or active channel width, but you get the picture of the kind of environment where these tend to work better. Here we're at close to bankful flow, relatively mild energy happening within there. And in a system like this that may have been small gravel, you put in large cobble into small boulders, they tend to stay. Here's an example of an active channel. The solution, this is in the South Bay near San Jose. And again, my experience is a lot of the active channel solutions fail. How quick they fail often depends on how soon does the large storm arrive after implementation. You can see here, so originally here's kind of some sheet pile. They had a combination of sheet pile weirs and concrete weirs here that were designed to hold sediment back. These were, at construction, these things were completely buried in sediment. There was about 6 feet deep of engineered stream bed material, which is just a fancy word for kind of calculating the size distribution of the sediment you're using in a design. So we had about 6 feet of sediment at the edge, kind of a trapezoidal shape to the channel. Here, these pictures are at about 50 CFS, which is actually a little lower than the active channel width. You can see the water up to the kind of last little bit of sediment that is left. And this is 2 years after implementation. Those photos are in 2017. This project was built in 2015. So here you can see the last remnant of sediment that was kind of sediment went from sort of bank to bank across here. This project attempted to deal with grade control issues here. It did nothing about the Sac Creek on the boundaries. So they had a deformable boundary within the channel and then hardened outside. So anything out of the active channel width was erosion resistant. So the first high flow that came in here pretty much scoured out most of the sediment. So I'm in the process right now of coming up with a whole new, working with these folks to come up with a whole new design on this project, and we're 4 years after a multi-million-dollar project being implemented. Again, that is sort of your worst-case scenario active channel solutions. Hydraulic design options. Again, as I mentioned earlier, here you're trying to match generally a fish's swimming and leaping ability with your hydraulic conditions within your crossing. This takes a fair amount of calculation for knowing your hydraulics at your fish passage flows. Rick's going to talk a little bit in depth about how we determine your high and low fish passage flows. So accurate modeling of the hydraulics and then seeing if they match to a fish's swimming and leaping ability. These, by and large, we're finding tend to be unsuccessful. A lot of it has to do with maintenance. Generally, hydraulic solutions require a lot of maintenance, and we're not talking just after large floods, but really on an annual to even semi-annual basis to keep them clear and keep the hydraulics performing properly. I think this is us on, is that middle?
Yeah, it looks like it.
I think that's Middle Creek here. Hydraulic solutions, there's a large suite of them. Often they are baffles within a culvert, concrete, steel. They tend to look nice and shiny right after installation. A few high bed load transport events later, they don't look like this anymore. They often also contain some level of trying to backwater the outlet to get fish up and in. For a long time, the standard approach for our hydraulic solution was to create fish ladders. And now, by and large, both DFW and NMFS have moved away from these approaches. These are really difficult to get the hydraulics right at a wide range of flows. And when you don't have a fish passage solution working at a wide range of flows, you really preclude the timing of the fish when they can move through. These are also phenomenal debris catchers. And they get full of debris and then they quickly become nearly complete barriers. So I can't go back, but one of my points that I forgot to mention on the hierarchy of solutions, if you notice, hydraulic solutions were number 5 on the list, last from basically DFW and NMFS perspective, but it's often the first suite of solutions that people look to address their crossing problems. They're generally the cheapest. They're the ones that a lot of people are most familiar with, and for a long time the paradigm in fish passage was to implement hydraulic solutions. So want to make that point that, at least from the fish agency's perspective, it is not the preferred option. So moving towards geomorphic assessment and risk, we'll talk first a little bit about size channels, nick points, how they move upstream. We'll talk about how to assess your vertical adjustments, basically your long profile. Get into a little bit about lateral channel adjustments, what to look for, and then talk about sediment. In size channels, pretty much, we're Caltrans here, we're just talking about California. Pretty much ubiquitous across the landscape. Any river system that has had some level of anthropogenic impacts to it generally exhibits some level of incision. When I'm heading out to the field, yes, I'm looking to identify is there an incision or not, but ultimately I'm trying to address what's the magnitude. Can I treat this? Can I work with a solution that can actually reconnect my channel restoration with the floodplain, or am I, if the incision is so deep, such as here with Billy, it's twice over his head, to reconnect the floodplain. In this kind of situation, you're working within, you're not trying to reconnect. Here's sort of your kind of classic headwater stream type of incision, where it's not as pronounced, but you can see the root masses kind of hanging over. This is North Coast headwater stream. So why do we have channel incision? It's both an anthropogenic induced phenomenon as well as a natural one. But human anthropogenic effects generally include channelization, where you shortened and steepened a channel, any kind of channel confinement from roads to levees, increases in discharge, decreases in sediment supply, dams and gravel mining, particularly in California, and loss of wood and other roughness elements. When you take those out of a system, you tend to stop your sediment retention, so sediment moves through quicker. That leads to channel incision. Natural causes of channel incision include drops in base level, which can both be caused by tectonic activity as well as differences in morphology. So, you know, things like Niagara Falls, that's natural channel incision. It is a natural evolutionary process. How does channel incision move through a system? Generally as a coherent nick point. It doesn't always look like this as a pronounced thing in the profile. Sometimes it can be a little bit, if it's not very consolidated sediment, it can be a little bit more laid out and not such a vertical face. This diagram here from Mike Love, a pretty classic thing that you'll see in the Central Valley, Central Coast. When you have a large dam that is really attenuating sediment supply, generally the dams are on kind of more main stem systems that are near complete traps of coarse sediment. This causes the main stem to incise. And you could be in relatively pristine tributaries to the main stem, but this drop in base level over here at the confluence causes that change in base level causes a nick point to migrate upstream, and you can end up in an incised channel in a relatively pristine tributary. One aspect of when I am assessing channel incision is I'm trying to look at the history of why is there channel incision. When did the road crossing go in relative to the impact that caused the channel incision? Essentially, I'm trying to assess, was this crossing built pre or post the incision moving through the system? Here's kind of your classic, this is sort of the poster child of what a road crossing can do in a system that's incising. This is in Mississippi, this is an Army Corps photo. Rampant channel incision downstream of this highway and these couple box culverts. Road crossings often act as phenomenal grade control, and they arrest channel incision from moving upstream. So here you can see this rampant problem downstream. I'm sure we want to call that a pristine channel upstream, but at least it's not incised. So if you were to, if you determine these things were undersized or outdated, if you were to remove those, your risk is letting all this incision you have downstream rampantly propagate upstream. So here it was obvious crossing went in pre-incision movement upstream, but it's not always the case. So how do you assess it if the situation doesn't look like that picture? It's generally with the long profile. The long profile is sort of the #1 tool to evaluating incision and your incision risk. Almost all culverts have some level of scour at the outlet. Here's just localized scour. This problem is relatively easy to address when you're designing a new project. Whereas here, we have both the local scour and kind of systemic incision downstream. This solution, this is from DFW's manual, call it long. I would tend to say it's complicated. There's various approaches you can take to dealing with this incision. But the only way to really tell if you're in that situation versus this one is a long profile that goes adequate distance downstream. If I could kind of leave one take-home message, that is, for Caltrans projects and design process, we need an adequate long profile. It needs to, in almost all cases, go way beyond your right-of-way. A standard rule of thumb, something like 20 times bankfill width. Sometimes that's more applicable than others. But most projects I see do not have an adequate long profile. We'll go into that a little bit more. In addition to the long profile, we'd like to see something called a vertical adjustment profile. This is sort of putting the bounds on your existing profile and your design long profile where you could end up in the future. You're trying to determine what is your maximum degradation potential relative to your design profile, as well as, particularly in a case where you might be looking at releasing sediment from the crossing, we have something called a high adjustment profile, the dotted red line. You're trying to look at what's your risk from aggradation in the system. Here's sort of a few elements that we tend to use for a vertical adjustment profile. Rather than really trying to, this can take a bit, I really like to point folks to DFW's restoration manual. Volume 2, Chapter 12, it has a phenomenal write-up on project profile design. There's about 15, 20 pages on talking about vertical adjustment profiles. About page 15 of Chapter 12. Very highly recommend reading that before you begin the design process. But some of the few things we're using for a vertical adjustment profile include your pool scour depths, you're looking for the nick points, you're looking for, you want to know your bank full and floodplain elevations, using things like debris jams. Debris jams often cause discontinuities in the long profile. So you need to go out and look at all these things, take notes of them, measure a few elevations, and you can kind of piece together your vertical adjustment profiles back like this. Some examples of long profiles, and talking about really what is hitting home the point of needing to have adequate lengths. This was an early conceptual diagram given to me by Caltrans on a project. And this is kind of the classic approach where here we're dealing with, this is a historic kind of rock culvert that's coming out for a full span bridge. There are some scour issues at the existing crossing. There's a point downstream. Here's our hole we're trying to fill and bridge. We look at our point downstream. Okay, here's where we want to connect it. How do we get from A to B? This was presented to me with another solution, and it was, what's your opinion? Which one do you like? Do you like the rock weirs? Do you like the roof bods? I am totally missing geomorphic context here. I do not really have slope of the design, but I don't know what's happening downstream. I don't know what the channel slope is here. I don't know what's happening upstream if I'm looking at aggradation or maybe incision up here. Again, no slope. Really hard for me to weigh in on what works here. But this is at the stage when we're developing potential channel design. So the next iteration that came through, really a couple weeks later, this is the same project with the same boulder weir design. And this is generally about the level of long profiles I see in the actual design sheets. And what's its extent? It's basically the extent of the topo survey that was needed to design the structure and the geotech. So they went out early here, collected some data, long before any of the other agencies were involved, long before I was involved, and this is the extent of the survey. The actual channel design here is more than half the length of the full long profile. Again, while I can see more here than that first one, I'm still missing a lot of what I need to really evaluate what is the desired solution here and what is kind of needed for having a long-term successful project. If you look downstream right there, here at the OG, you can see a little bit of a discontinuity in the slope there. It's hard to see at the scale, but it's almost 2 feet that's dropping right there. I don't know at this point, is that a nick point? Is that a pool that just doesn't have adequate shots, topo shots in it? But it's not hard to imagine that there's another one of these right here. You often see multiple nick points in the system. If there is another couple more of them, as soon as this crossing comes out, they're likely to be moving upstream, and you can see already we're going to compromise the depth of the boulder weirs. When you start bringing up scour through the boulder weirs, pretty common to lose the downstream one. This is the downstream one that goes off in the whole project on zips. It's really a plug for folks in the room to early on set aside the budget and planning to get an adequate long profile upstream and downstream of your project. It is really paramount for successfully designing a long-term solution. Here's an example from Mike Love of what I would consider as an adequate long profile, maybe a little more so, but it has about 800 feet of survey downstream of the crossing. This is concrete apron at a historic bridge. You can see though from this, though we can clearly identify what is systemic channel incision, about 3 feet here, another foot of scour below the apron. I can adequately see that the slopes upstream and downstream are equivalent. And it's also, you can see if he didn't go all the way down here and you attempted to just draw your downstream long profile in this suite of shots here, you end up with different conclusions. Lateral channel assessment, time series. I'm not going to step through something, an analysis I did on lateral channel migration. Am I doing fine on that?
9 minutes.
9 minutes left? This is the Russian River. This is an example of a bridge that failed in 2006. Here is the new bridge being built. Aerial photo, flow, moving upstream, downstream. And so this is kind of my assessment, just stepping through Google Earth time series. 1993, this is the original bridge. You can see, looking upstream here, the meander scars and vegetation lines of where the historic channel was occupied. And right away you can see bridge abutments are inside the meander scrolls of this channel. And the other thing that's pretty obvious is the bridge is kind of skewed to the primary valley axis of the Russian River here. This end's kicked up. By 2003, there's quite a bit of right bank erosion happening here. The vineyard's starting to go away. 2006, in the New Year's December 2005 flood, this bridge fails and overtops. And what happens right afterwards, emergency repair happens and build a brand new shiny bridge in the exact same configuration and geometry that the original one was. The abutments have stayed in the same place. The channel skew is still there. And the problem with the channel skew here, there's 5 or 6 piers underneath this bridge. When those piers are oriented at the direction of the bridge, they essentially act like bedload transport vanes. So think of it as the airflow vanes in your AC in your car. When you move those things back and forth, it redirects the air. The piers sort of act the same way. They're controlling the trajectory of bedload transport and scour here. So we're pretty much always going to scour and transport this direction. So this river that used to formerly flop back and forth within its floodplain here is pretty much always going to have an axis that looks like this. This leads to increased bank erosion on the outside bend here. 2008, and this is a higher flow, but you can kind of get the sense here that we're starting to scour more this way. This abutment's starting to become compromised. 2010, first round of riprap goes in to try to save the abutment here. You can see the vineyard continuing to go away. Again in 2010, at this point, the erosion sort of declared mission critical here with the scour behind there as well as here. So another multi-million-dollar emergency repair happens now. Riprap this entire area up here. Put in some lateral deflectors here with riprap and kind of lock in the thalweg here. Again, the same problem. We have basically pinned the channel right there for the foreseeable future. And we sort of lost our lateral migration. The sediment transfer system, a lot like the earlier diagrams, it's kind of a schematic of where we produce sediment in the headwaters. Your mid-valley reaches, we consider these transfer reaches where sediment transport capacity is high. Generally, all the production up here moves through rapidly, and then we have our depositional zones. Understanding where your project is in the schematic is another important component of successfully designing a project. If you put a boulder weir system in here, you're going to probably do well in maintaining your pool scour depth, but you're also going to struggle to keep your boulder weirs in place over the long term. Here we have high sediment transport capacity, so the river channels can continually mine the bed of sediment, often plucking some of your rocks that are holding your boulder weirs in place. Down here in a sediment depositional zone, your boulder weirs are probably going to have a much longer life, longevity, but again, they're going to fill up with sediment, and pools are your main objective here. Just sort of a photo of the schematic from before, trying to appreciate the amount of sediment that are moving through river channel systems and the exchange, the deposition and erosion that happens with the floodplain, mining of the channel bed sediment, bank erosion is a natural source. If you cut off any of these supplies, if you disconnect from your floodplain, well, the river channel is going to make up for it by mining your bed sediment. Same thing if you riprap banks and stop the bank erosion from happening and disconnect that source, you tend to increase the amount of sediment that's mining the channel bed. So it often comes to the question of culverts generally, when they're many times when they're undersized, they are sediment traps upstream. You get aggradation happening upstream in the process. So there's kind of, if you're replacing that culvert, opening it up, you are often having to address the question, do we release the sediment that's stored upstream in the culvert or not? First order question is to answer, what is my situation? Is it just localized aggradation happening upstream? Or is it such that it's really it has a great control that we have systemic aggradation happening upstream, and the upstream channel has likely adjusted its banks to this deposition? How do we know which one we're in? Adequate long profile, going up far enough upstream. Sort of stepping through the process of how I would assess whether to release the sediment or not. First order is to quantify the volume of sediment stored upstream. And then I compare it to what is the average annual load of that system. This can be calculated at the scale that you need for this kind of assessment with some USGS regression equations. USGS has some manuals out that work a lot like your regional Q100, Q50 type of calculations, where if you have drainage area, annual precipitation amounts, you can come up with an annual load. So you're trying to figure out, most culverts are going to have less than 1 or 1 year's worth of sediment, about your annual load. Well, that's basically one large storm. That's typically inconsequential to a river channel system to release about an annual load's worth of sediment. But you do want to look at what's your accommodation space like downstream. Can you handle that? Am I in a sediment depositional zone? Well, if yes, then your sediment might go a few feet below your crossing and stop. If you're in a transport zone, it's likely going to move through very rapidly. Are there other biological concerns? If the whole upstream channel has adjusted to the sediment deposition, am I going to create unstable banks upstream? And also the size distribution. Culverts are really often act as really inefficient dams. Here's a schematic of what a delta deposit looks like behind a dam, where you have your bottom set beds of really fine sediment, a force set bed of coarser sediment, and then upstream on your top set bed tends to be really the coarsest fraction of the load. In a culvert, because they're really inefficient traps, all this fine stuff tends to flush right through. So usually your sediment upstream of a culvert is biased towards the coarser fraction, often the stuff we like from a biological perspective, coarser responding type sediment. It also can mean it's harder to transport if you're in that depositional zone, since it is biased towards the coarse fraction. Looking at geomorphic design principles, pretty straightforward. There's sort of three main caveats of it. One is Minimize what you're doing, protect the natural form, maintain your geomorphic processes, try to optimize whatever you're putting into the river channel to create natural functioning things, pool, scour, sediment sorting, channel migration. We try to passively or actively create these features through wood structures, pools with self-sustaining scour mechanisms, things like that. This is sort of just a reproduction of that flow chart I started at the right at the talk's onset. We design down here. We look for making certain cross-section shapes and longitudinal profiles. Sometimes we work with trying to come up with a specific plan form element. But if you have underappreciated both your boundary conditions as well as your inputs of flow and sediment fluxes to the channel, you are really unlikely to successfully create in the long term a particular cross-section shape or long profile. How do you do this? I like to look at it as first starting with a reconnaissance level, going out into the field, finding your reference reach, finding out what works, what is working, what are the forcing mechanisms that are naturally occurring, and essentially trying to replicate that reference reach. Rather than going into a certain channel predetermined that you're going to make boulder weirs or root wads, if that's not what's actively working in the system, don't necessarily try to replicate it. Then down here, Rick is going to really cover modeling in his talk, but you need to actively look at what is your sediment transport capacity. What are the stages that your bank full discharge, your Q10, and even higher flows. So modeling needs to be a component of it. This is Mike Love's slide here. This is how he steps through coming up with a fish passage design. He figures out his objectives, sort of does a rough sketch, goes out in the field, does a site assessment, comes back and calculates the various risks, lateral erosion, his vertical adjustment profiles, determines what is the alignment he's looking for at this project. And then at that point, he looks at finding a design approach to achieve that alignment and profile. Here is where I find myself often with working on Caltrans projects. I get brought in and selecting a design approach. A few different design options are presented to me, and we're trying to figure out what works best without having really gone through and determined what we wanted, and really what the risks were up here. Bringing that geomorphic design approach into a few other topics, using habitat improvements and mitigation. Have been involved with multiple conversations where the project is disturbing X linear feet of stream bank, and so that then equates to, well, let's make that X number of boulder structures and X number of pieces of wood, and we're fixed. It hasn't, that ignores sort of the geomorphic design approach, rather than going into a river channel and figuring out what does this system need, if anything, and kind of determining it based on that versus just basing it off a linear channel disturbance. This is also on the South Bay project. I'm looking at a flood control mitigation plan where the NIMS buyout basically determined that, I can't really tell you what the rhyme or reason was, there's going to be X number of wood structures and boulder habitat enhancements done for this project. So the design comes with basically installing just root wads everywhere. We think that erosion forces could be high. 3 boulders cabled in epoxy together in the river channel at regular intervals. Approaches like this don't necessarily create the habitat diversity you're looking for or have long-term success, and really can lead to a mess of cable and hardened structures in the river channel rather than good. Bringing geomorphic design process into scour repair projects. I probably see more scour repair projects than fish passage projects working with Caltrans. In a scour repair project, usually starts with how do we fill the hole? What's the biggest rock we can stick in that hole? Can we grout it over? Without really figuring out what caused the scour in the first place, what was the process that led to that? Can we address that? Can there be some sort of geomorphic design to redirect flow in a more beneficial way? And if you don't tend to include your geomorphic processes in your design on a scour repair project, well, they'll kind of come back and they'll do their own thing and create scour either downstream of your project or at the project site. This initial solution here at this kind of mission critical scour bridge was to just fill the entire channel with riprap, footer to footer, across the whole channel. Basically make a 6-foot wall of riprap downstream. We were able to persuade them to take a different approach, essentially encase the abutments and footers here with steel and pump them full of concrete this vertically, and then created a rock ramp starting way down here that goes up to about the base of the footer there and daylights at the top of the footer here with this roughened rock ramp channel. Blue line versus green line fish passage. The kind of the value of lateral channel access to off-channel habitat. Fish passage generally likes to talk about and think about moving fish in one beat up this blue line channel to presumably something greater upstream. There's not a lot of discussion about how do we make sure we have fish passage laterally out onto the green field. We're finding more and more how important getting fish out onto floodplains is really, it's the key component for successful indigenous fish runs. Can your stream crossing affect greenfield fish passage? And I would say yes. If you go back to the Russian River example here, where you sort of lock the channel in over here, we've decreased our overbank duration and frequency of flooding, as well as really going to alter what this habitat out here looks like if it doesn't routinely receive flow and the channel moving back and forth. Is stream simulation enough? Basically making your design capture the bankful channel width. Here's your active channel, here's your bankful, here's your floodplain. If we're just at the bankful channel, can you impact greenfield fish passage? And I'm going to kind of walk through an example of showing you how yes, you can. I looked long and hard for an alluvial channel in California that really didn't have much anthropogenic impact. This is on the Lost Coast, Steelhead Stream, Big Black Creek. I'm going to go through a time series, just pick any meander bend in this series and just focus on that one and watch it over the next 10 years. And so you can see that within a 10-year period, pretty much every meander bend there swung across the valley axis. That's sort of what you can expect in the dynamic alluvial travel system. This is an example, this is called Millerton Gulch. This is in Tomales Bay. Here we have a crossing that is nearly the bankful width. But when you pinch the channel here at one spot within the valley width and don't really span it, what do? The same 10 years, channel stays in the exact same place, it's unable to migrate. This channel, particularly up here now, is really oversteeping. We have a bunch of real steep clay banks, probably going to have some more erosion problems up here, already had scour problems there. And now we've decreased our frequency that fish can get up onto the floodplain here as they head out to Tomales Bay. And sort of more examples of what Millerton Gulch looks like, a lot of erosion problems on that far valley side, sediment deposition in the inner bend box. And that's kind of it. I really would recommend taking a look at DFW's restoration manual. There's a few other excellent resources out there to help you design projects. And contact Rick and I early on.
Thanks, John. All right, we asked John.
This is another really important component of your pre-project design. This diagram here is in some kind of classic channel evolution model where you start with your equilibrium channel. You have a little bit of incision comes upstream and you oversteepen your banks. That oversteepening disconnects floodplains, and so you get more scour. Eventually the banks get so tall and oversteepened they collapse and tend to build a channel within the channel. And we now have very low floodplain, original floodplain connectivity that turns into a terrace, and we sort of have a new floodplain. But trying to figure out where you are in this schematic in your project really should influence your design. So what are we doing in the field? We're looking for multiple active active channel, bank full channel measurements. You're looking for your valley width. You're identifying floodplain versus terrace. We're looking for bank erosion, and if you have bank erosion, why? What's the cause of that? Generally looking for bank erosion on both. You have it on both sides. Do we have evidence of overtopping the bank full channel? Is there floodplain connection? And probably one of my favorite tools now is use historical aerial photos. This is now really generally a pretty easy exercise with Google Earth. Here's where you tend to see this is where you find your meandering and island braided type of systems, where kind of 1% slopes or less. Main difference here between a meandering channel and island braided, usually this is a single thread system. Island or an anabranching or anastomosing type systems have multi-thread. You can see that naturally these kind of have a high floodplain connectivity. Trying to establish a stream crossing in systems like this is very challenging. Often in this type of system, we like to grab one channel and try to make it the dominant one. Down here in a meandering system, at the time of establishing a crossing, often there is a clear-cut single-thread system, but when you do that, many times you isolate yourself from accessing a lot of these remnant channels here. We call those oxbow channels. Those tend to provide excellent high-flow habitat for several aquatic species. So many times, both combinations of roads, levees, etc., like to isolate this overbank habitat.